we're going to be covering something called the axiomatic probability theory. Okay, in axiomatic probability theory, for the first thing that you need to understand is something called the experiment. Okay, you need to know what exactly the experiment is. Experiment is nothing but a process. It's a process of generating some observable results, okay, called the outcomes, such as or such that the total observable outcomes, possible results, I don't know why it's happening, possible results can be completely specified before conducting it, okay? Where I think, yeah, the TSOA is nothing but the set of all, okay, the set of all possible results. So, we do something called trials, okay? You remember, like in probability theory, we do trials. So trial is basically nothing but a single performance, okay, of an experiment. And you have something called the sample space, okay? And sample space is nothing but S, which is TSOA, again, the set of all possible outcomes. So sample space consists of, all possible outcomes. Example includes, tossing of a coin, okay? Tossing of a coin 2 times. So when you toss the coin 2 times, obviously there are only 2 outcomes. One is head, okay? Other one is tail. So the sample space can be head, head and tail, tail and head, and tail, tail. Okay, so the 4 possible outcomes, all of them included, and that will be in the sample space. You toss until the first head comes, okay, that could be considered as sample space. You can actually have sample space based out of that, so it could be head, tail, head, tail, tail, head, it could be countable infinite, okay? So toss until the first head comes. So you can keep tossing it, you can keep putting it in the sample space. There's going to be infinite possibility like that, okay? The other example that I can give you where the sample space can lead to infinity is pick a light bulb at random and observe its lifetime, right? So that S3 is going to be x of s greater than or equal to 0, which could be 0 to infinity, right? And that's uncountable. So there are other things that you need to know, like in probability, some of the definition could be like C, which can be denoted as a subset. U is nothing but union, and the interaction, which is inverted U. These are, some of the symbols that you will be seeing it in most of these probability theories. The other thing I would want to say is that an event, you've heard a lot of things about event. Event is a subset, okay, of a sample space. Okay, event is a subset of sample space. Now, for any event A, B in S, there are certain possible things that can happen. One is that A is equal to B if A is a subset of B, right? And B is a subset of A. The other condition that you can see is that A union B, which is again can be written as X is an element in the whole sample space, where X is also an element in A, or X is an element in B. Okay, so those are the conditions that can happen. The third thing that can happen is A interaction B, which is nothing but X, which is in the sample space, where X is an element of A and X is also an element of B. Okay, there's something called A complement. Okay, you must be seeing this complement of A, which is nothing but X in a sample space X, where X is not in a sample or not an element of an event A. Okay, it's anything outside of the event. The other thing that you will see, obviously, you'll talk about something called the Venn diagram. You know, you have A and B. Okay, so A union B, you can write it down like this. Obviously A interaction B, is that A union B consists of all of that. Okay, but you know that the A interaction B is a subset of A union B, right? So those are kind of, again, the theorems that you should know. There are a lot of other theorems that you can also derive. I don't want to talk more about it, but these are the things that you probably be able to write it down. A union B is nothing but B union A. Okay, if obviously those are the events, right? You can also write A union B, combination of B union C as A union B with the brackets in, and then the union of C. Okay. There are something called, again, the distributive laws, and there's something called the De Morgan's law. I'm not going to go into the detail, but I'll just give you the idea behind De Morgan's law, which is A union B complement is nothing but complement of A intersection complement of B. Okay, it can also be written as AB intersection A complement union this. Okay, that's De Morgan's law. Let's talk about the other stuff, like in terms of the events. There are a lot of things that you need to, again, cover. There are a lot of things that you can write it down. Let's say that you have A of T, where T is basically a subset of this. It's being an event, okay, in S, where you have union of T intersection. That's the union of A of T, where T is an element of capital T. Okay, so X is basically in all the sample within S. X is also an element of A of T for at least one T, which is again an element of capital T. Okay. You can also write intersection of T as an element of capital T, A of T as the intersection of A of T, T as an element of T, okay, which is X is a subset of X is a subset of capital sample space S, where X also exists in the A of T. Okay, so those are probably some of the things that you should know in probability. Again, I'm not going to go into the details, but these are some of the axiomatic probability theories that you should know.